The latest version of Proto Twin includes some big upgrades to the Connect application with brand new and exciting features. So let's dive right in. ProtoTwin Connect now supports a number of additional platforms. If you navigate over to the account page on our main website, then click the Download Connect button, you will now be able to download the application for Windows on x64 and ARM, macOS on Apple Silicon, and Linux on x64. In this first example, I'll be using ProtoTwin's macOS Connect application to demonstrate connecting to a Siemens 1200 series PLC. Once you've configured all your properties for the tag server, you can then click Save. Once you've done that, you can click the Import button to import the PLC tags directly into ProtoTwin. After creating the bindings, we can swap over to the bindings table and configure how each tag is bound to a signal in our ProtoTwin model. You just need to specify an entity, one of its components, and an I/O property of that component. Once you've done that, you can now run the simulation to test your PLC program. The bindings tell the ProtoTwin client which I/O points in the model are connected to which PLC tags. The values are then transferred back and forth from the PLC to the Connect client, enabling real-time, low-latency communication with PLCs for virtual commissioning and controls testing. In this next example, I'll be using the Connect application again, this time running on Linux, to demonstrate connecting to a Raspberry Pi using the OPC UA protocol and code assist to control a simple linear axis. After creating your tag server, you can click the Import Tags button again. This will launch the object browser. You can then navigate the OPC UA node tree for the server and select the nodes that you wish to import as tags. Now we're ready to create the bindings. The actuator tag will be bound to the state of the push button component, and the current position tag will be bound to the motor's target position. The last thing I need to do is add a signal converter to the current position tag. The value on the server is specified in millimeters, whereas ProtoTwin uses the units of meters by default. The motor that's bound to the joint in our model has the controller set to none, meaning that ProtoTwin is not doing any motion control here. The motion of the axis is controlled entirely using code assist. We've made a number of improvements to the Connect application for reinforcement learning. The latency when connecting to Python has been greatly reduced. You can now also disable the rendering. This has a noticeable improvement in performance when stepping the simulation. You can enable the rendering again at any point to check how well your model has learned to solve the problem. The vectorized environment for the agent here is tasked with moving the drone to a random target position. We've thoroughly tested reinforcement learning on Windows, Mac, and Linux. We've added a brand new color sensor component to the application. In this example, I've created 3 entities with 3 different colors to demonstrate using the new color sensor component. I'll first go ahead and add the component to the white box. Just like with the distance sensor, we need to configure the origin of the beam, the direction, and the maximum detection range. The component stores an array of colors. This property represents the colors that can be detected by the sensor. The tolerance property is then used to determine whether a color has been detected or not, based on a distance metric from the measured color. The color sensor has 2 I/O points, one for the state, which is true if a color has been detected, and false otherwise, and one for the color index. The color index is an index into the array of colors of the closest detected color and is -1 if the sensor can't detect a color. If we move the box towards the blue entity, you will notice that the color index changes to 1, since blue is at index 1 in the array. Notice how the color index changes accordingly as we move the box. I'll now demonstrate a more practical, real-world example of how the color sensor can be used in accordance with a line-following robot. The line follower robot has a custom scripted component that controls each of its 2 wheels. The script also references an array with 8 color sensors. I've already configured the properties for each of these 8 color sensor components, which are set up accordingly to detect the color of the line. Based on the state of each of these sensors, the robot outputs target velocity commands for each wheel. I'll now provide a quick overview of the script. The script references the motors of the 2 wheels and an array of color sensors. A PID controller is used to control the wheels. The current value is determined from the state of each sensor, which then gets fed into the evaluate function of the PID controller. The control value is then used to adjust the speed of each wheel accordingly. If we now swap back over to navigate mode and run the simulation, you should see the robot begin to move along the colored line. Every time step, our script is reading the state of each color sensor, determining the current value based on this state, then evaluating the PID controller and using the control value to determine the speed of each wheel. For such a simple script, the robot moves remarkably well around the sharp corners of the track.